Welcome to the second in a series of videos on stereoisomers, recognizing them, identifying them, naming them, and their uses. As has already been shown, stereoisomers are types of organic molecules that, as all other isomers exist, are different compounds that have the same formula. In the case of stereoisomers, you also have compounds that have the same structure, which means that they only differ in the arrangement of the molecules, essentially of the atoms rather. Essentially, a stereoisomer is a type of a geometric isomer, which you have seen before. If one has sp2 hybridized carbons, where you have a carbon-carbon double bond, a different arrangement can give you cis or trans isomers. In the case of an sp3 hybrid carbon, where you have nothing but 4 single bonds, you get chiral centers if you have 4 different substituents attached to those bonds. The latter gives rise to what are called optical isomers, which, as has been mentioned, bend the plane of polarized light either clockwise or counterclockwise. These types of molecules were first looked at by Emil Fisher around 1900. Fisher noted that looking at one particular molecule, glyceraldehyde, sometimes it bent light to the right, sometimes it bent light to the left. He looked at this molecule closer. This molecule, which today in IUPAC would be known as 2,3-dihydroxypropanal, was an aldehyde with 2 OH groups. Fisher noted that that central carbon, carbon 2, actually had 2 different ways that one could draw it. Okay. So he devised a way of doing this called Fisher projections. Essentially, what one does is take the original molecule and flatten the plane. In a line drawing, leaving out all the hydrogens, the 2,3-dihydroxypropanal is bent. That second carbon is chiral, which means that the hydroxide could either be on the left side or the right side. Fisher noted that when the hydroxide was on the right side, he got the plus or the clockwise rotational isomer. He denoted this as the dextrorotatory or D isomer. So one had D for dextrorotatory plus for the direction of the light bending clockwise glyceraldehyde. Similarly, the only other way of drawing this, with the OH on the left side of the projection, corresponded to the negative or counterclockwise rotation of light, and he noted that as the levorotatory or left-handed bending isomer, so that would become L minus glyceraldehyde. In general, the Fisher projections only depend upon the second carbon and its position. In a Fisher projection, whatever the carbonyl group is winds up on top, if it's an aldehyde, a ketone, or a carboxylic acid. There's also a terminal group on the bottom in all of these biomolecules that has an alcohol. In the middle, the only carbon that is necessary to determine D or L is carbon 2, based on the position of an OH or an NH2 group. Between carbon 2 and the terminal carbons, there could be any number of other carbon groups attached. So, if the OH is to the right in the Fisher projection, it becomes the D isomer. The other possibility, looking only at carbon 2, is that the OH or the amine group could be on the left, which, according to Fisher, is the L isomer. This works out quite well, except it has one major problem. Fisher projections, however, have a problem as molecules get bigger. If one looks at two different molecules, on the left, you have the D isomer of glucose, dextrorotatory because the hydroxide group is to the right-hand side of the Fisher projection. Also, you can see another molecule that is a D isomer, the D ribose. However, when looking at the optical rotation of these molecules, glucose indeed matches what is supposed to be shown. The D-dextrorotatory structural isomer is actually the one which rotates polarized light clockwise. It's the positive optical isomer. In the case of the ribose, however, for some reason, which you will see later, this correlation falls apart. The as-drawn dextrorotatory isomer actually bends light counterclockwise. Essentially, even though that was a good effort, the Fisher projections don't actually match what nature has shown. The dextrorotatory geometric isomer is not always the plus optical isomer. The laboratory geometric isomer is not always the counterclockwise negative isomer. This is due to the fact that the molecules go past the second carbon and that the total net electric field depends upon the result of all of the chiral centers. This net field is what determines which way the light will indeed rotate. In the next video, linked in the description below, we'll look at a more precise way that was developed to name these stereoisomers and investigate more how closely those will correlate to the actual behavior of these isomers when exposed to light. Thank you very much for listening, and I hope you found this useful.